Hello everyone and welcome back to your YouTube channel and welcome to this very amazing video today. The lovely video today is related with this course about electromechanical conversion systems. And as you must be aware, when we are working with these electromechanical conversion devices, rotating machines, they are extremely important. If you think about the electrical power system, we will find rotating machines in both extremes. On the generation side, you will find the generators producing the electricity coming from a mechanical source. It can be hydropower, it can be thermal power, or even nuclear power, who knows. However, on the consumption side, on the demand side, you will find those motors. And motors has been the most important element to produce mechanical power to deliver the industrial revolution. So what I'm trying to tell you is rotating machines, they are extremely important. And for many years, DC or direct current machines, they has been playing part on the motor side. And today we have an exciting video related with some calculations for the DC machine. In particular, today we are paying attention about the armature structure and the winding type used on the DC machine. But without further delay, let's start with this exciting video today. And in front of you, you have here this amazing statement. We have a very practical and numerical simple example. So let's start. A 4-pole DC generator has a lap wound armature with 40 slots and 16 conductors per slot. And the useful flux per pole is 50 milliwebers. So there is a very interesting and exciting question here. Determine the rotational speed in revolution per minute, also known as RPM, at which the machine must be driven to generate a MMF of 400 volts. So here you have the answer. As you can see, the answer is, well, this lap wound armature must rotate at 750 RPM in order to produce 400 volts. So if you want to try this solution, please take your time and start by the equation, look at the equation, and of course, I wish you all the best in this attempt. However, if you are short of time, you can go to this very quick explanation that I will be running here for you today. Well, when we are talking about the physical structure of the armature, and when we are talking about the induced voltage in the armature, this equation over here, equation number 2, is extremely important, because it's telling you that the induced voltage armature, E, in volts, is numerically equal to twice P is the number of pairs of poles, and this Greek letter is the rotational speed in revolution per second. So be careful, because the answer is in per minute. And phi is the useful flux per pole. And Z is the number of armature conductors, and C is the number of parallel paths through the winding between the positive and negative brushes. So as you can see, I will tell you that the two more important aspects that you need to pay attention, especially regarding the structure and the type of windings, are Z and C. This is because Z and Z set and C depend of the type of winding that we are having in this amazing armature. So think about the theory for a second. So you must remember this slide from my classes, and this slide is extremely important. Because in this slide, you can see that I am presenting the two different types of windings that we can find in most of the DC machines. I must be honest, you can find others, but the two more popular type of armature windings are the lap winding and the wave winding. And when I say that you need to pay attention about this type of winding, is because they have very different physical and mechanical and electrical properties. So let's start here with the lap winding. The lap winding is quite interesting because, as you can see over here, in black color, I have the coil number 1. And number 1 and number 2 over here that I am pointing with the laser, you can see that this is the starting point from the coil 1, and then it's going to the point number 2, where the ending of the coil number 1 is connected to the starting point of the coil number 2. In other words, what I am trying to tell you is that this lap winding is also called parallel winding. And the reason that they are called parallel winding is because basically the coils, they are connected in parallel. So when we are working with low voltage DC machines, well, we use this lap winding if we are working with high currents. So as I said before, the lap winding can be found in DC low voltage machines where the application requires higher currents. However, the second type of winding is the wave winding over here. And you can see, let's see, this is the coil number 1, this is the starting point. You go through the North Pole, the South Pole, and then you go back for closing this coil. And that is the starting point of the next coil. However, you can see that they are connected several slots apart. So in this case, the wave winding is connecting in series the coils. So another name for the wave winding is series winding. And the reason is because we are connected in series different windings through the armature. And this wave winding can be found in high voltage DC machines, where this lap wave is the connection preferred because you are dealing with less current but with higher voltages. So I was explaining this short theory because if you are using a lap winding or you are using a wave winding, the electrical mechanical properties are different. So the induced voltage will be also different. So in this case, let me go back to my explanation and finishing solving this very interesting problem related with the induced voltage. So here we are again, and I was telling you how important is set and C. For C, for the letter C that represents the number of parallel paths, the solution is very simple because depending of the winding that you are using, you will have different values for this constant. For instance, if you are using the wave winding, you can see over here that the letter C, the parameter C, must be equal to, and if we are using the lap winding, like the winding that we are considering in this problem, C is equal twice P, where P is the number of pairs of poles. So it's clear that Z can have two different values, and those values will depend on the type of winding. So now let's focus on the solution of this very interesting problem. And as you must remember, we have the equation number 2, but this equation number 2 is used to obtain the induced voltage. However, the question in this problem is the rotational speed. And for that sense, we need to take this equation number 2 and extract from here the rotational speed. I already did for you, and you can see over here that the rotational speed will be proportional to the induced voltage, but inversely proportional to these terms over here. So let's focus now in the two very interesting components, Z and C. We know already that C is 2P, because here we know that this is a lap winding. So let's see what will happen with the equation, because we are working with a lap winding. And as you can see, when we put over here 2P here with 2P here, they cancel. And you can see now that the rotational speed will be basically the flux per pole multiplied by Z. And that is what I am presenting over here on the equation number 5. The equation number 5 is telling you basically what I already say, that the rotational speed depends of the induced voltage and is inversion proportional to the flux density per pole, the flux per pole, and Z, that is the total number of conductors located at the armature. So now let's focus on Z. The total number of conductors, there is an interesting equation. You can see over here this equation. And this equation says that the total number of conductors is twice C multiplied by NC. And NC is basically the number of coils. However, I have a really bad news, because for this problem, we don't know NC. So in this case, we need to be engineers, we need to be clever, and what we need to do is use the basic knowledge and understanding of conductors and the armature. So now, what I will do is something very simple. I don't know the number of coils, but I can use very simple logic. In order to obtain the total number of conductors, I know that the armature has 40 slots, and each slot is having 16 conductors per slot. So a slot cancels with a slot, and when we multiply 40 by 16, we obtain 640 conductors. That is the total number of conductors in the DC generator armature. And now we can solve this numerical problem by basic substitution. What I am telling you is that when we are done with this number, what we need to come back is to the equation, and the equation say that the voltage that we want, in this case is 400 volts induced in the armature winding, is divided by the flux per pole, and in this case this is 50 milliwebers and 640 conductors. You need to be careful, because if you remember, the units using that equation is revolution per second. And the question that we are asking in this problem is in RPM. So when we put the numbers inside this equation, we obtain 12.5 revolution per second. But this is not the answer, for our question, because we need to convert from revolutions per second into revolution per minute, because if you remember the statement, the question was the rotational speed in RPM. So here we are with 650 RPM. That is the solution. That is the rotational speed that you require in this very specific armature in order to produce the 400 volts. So just as a practical advice, be careful with the units. Every time that you are solving a problem, please try to keep the track of the units, because you will avoid by surprises. If you say that the answer is 12.5 revolution per second, you will be wrong, because in this problem we clearly state that the answer must be in RPM. So pay attention. And second, I would like to say that this is the sad part. We reached the end of this video, and in this video you learn how to calculate several features related with the armature winding. And as I tell you during the theory, the two more popular windings used for the armatures are the lap winding and the wave winding. Each one of them have different electrical properties, of course, mechanical properties as well, but in this video we use those properties in order to calculate the induced voltage. So this is the very end of this video. I hope that you understand the explanation. I try to do my best in order that you understand that. I hope that you learn about the DC machine and the armature and the windings. And if you have any question, please feel free to drop an email and I will be extremely happy to help you. But I need to say this is the end now. Bye now.